I guess most of you think we're here, which is to actually talk about models that actually can model the atmosphere and the weather. And so I'm really interested to hear what he's going to say about that.
Okay, thank you. First of all, I thank Hillary and the organizer to have invited me to the program and invited me to give a presentation at this workshop. So if you don't like it, it's their fault. And well, my presentation, I guess it's the closest one. I'm very surprised is that of Mark because talking about, as mentioned, real model that has done something that is close to what you want to achieve eventually, like variable resolution. So let me start. So very simple flow. First, numerical weather prediction. I will skip very quickly because I think by this time you probably know everything. Then I'll talk about the genesis of the current operational model at Environment Canada, which is the Global Environmental Multiscale Model, and how it evolved from the ideas of André Robert and Andrew Sanifort. And then the GEM model itself, and then two of its recent evolution. So operational model can change, and then some of the operational plan, and then some thought for the future. Here's the Earth, and well, I show that because it shows the complexity of the atmospheric system, and all we are doing is the dotted line. So we don't do the things that are really complicated, but eventually one of the goals is to have the people doing all these complicated things do it into our models. So a word about real-time weather forecasting. So first of all, it has to come quickly enough, because the perfect forecast of yesterday's weather is, especially if it's produced tomorrow, is completely useless. It has to be stable, because you don't want to wake up the operator in the middle of the night saying, well, the run blew up, what do I do? So operational numerical forecast, they should always reach the end. So we don't want random perturbation to eventually develop into a blow up or develop a large local error. So it should be at least conditionally and preferably unconditionally stable. And now on the point of accuracy, people are very proud of having high order methods that are more accurate. But I think I will say something controversial here. It's because computer architecture has evolved, and the memory systems are so slow that you can use the data that you have in cache to do higher order computation before putting them back to memory. Therefore, you get the high order free. But sometimes, on some of the problem, as the comparison that was shown by, I don't know who, I don't remember who, but comparing the meta-office model with, the German model with a distributed Galerkin that was high order, and there was almost no difference. So it means that this high order, in principle, is not seen by the model. So unless you use this more accurate per cell discretization to reduce the number of cells, this will not be seen by the forecast anyway. So the best forecast is the one that is just good enough. And I think that was mentioned a little bit earlier, that errors should be balanced. There's a time error, there's a time space truncation error, there's the model error, there are observation error, and also representativity errors in the measurement, and error in the analysis, and all of that makes that you're not trying to do a very accurate forecast like machine accuracy. You don't need that. What you need is to reduce, let's say, the spatial error, the time error, to the level of all the other errors, because if you reduce that lower, it's not going to be seen anyway. So that's one way, at least in our institute, we have optimized the models. Paradoxically is by increasing the time truncation error. So it's used for data simulation as well, and also for obviously it's just not the weather prediction, but all the coupling to the ocean and the environmental air quality and so on. So this is what I see here. So environmental prediction is important. So this is an old slide, but it's probably accurate. So at the end there it says that 50% of the activity in the world is sensitive to weather. Now weather, well, I was asked to do a bit of history. I should thank Janusz Pudikiewicz here for this quote, because probably the word meteorology comes from the Greek, and why? What does it do with meteor? Well, I think you have to think that for the Greek, everything that fell from the sky was a meteor, so it kept for the meteorite, but not for the rain. But Aristotle. We're not sure he looked like that, but he already knew the daily hydrological cycle. So all we have been doing for the last 2,000 years is to improve a little bit on that. Now I can, jumping to the 20th century, it's a very interesting, Cleveland Abbey was the first director of the American National Weather Service at the end of the 1900s, but when he left, he wrote this paper. And by trade, he was an astronomer, was trained in St. Petersburg, and he became director of the National Weather Service. But he wanted to have the weather prediction move away from folklore to scientific basis. And he wrote a paper and that described weather prediction as a problem in physics. So if you look at the AMS site, that's where they make the weather prediction begin. And here in Europe, but because it was about the same time in 1904, Bjerknes was a student of the famous mathematician Poincaré, and he was bold because he said, well, weather prediction can be cast as an initial value problem, and he described more or less the procedure that we follow to solve the equation. But Poincaré was a much smarter mathematician. So turbulence will set in, and you won't have enough predictability in your system. Something that was discovered a little bit later by Lorentz. Now Richardson, very interesting, can spend half an hour talking about him. But he was, how do you say, he worked with the Red Cross, the ambulance, during World War I. He spent about 2 years there, and he used his spare time to tackle the full equation with numerical methods, with hand computer or mechanical computer, It's estimated that it took about 2 years to make a forecast, and it was a monumental disaster. And it was such a disaster of monumental proportion that it prevented people it discouraged people from trying to solve these equations for about 50 years or 30 years. But he was a very clever person, and he foresaw parallel computing. He wrote a book about that. So following this miserable failure, Rossby made some progress in understanding atmospheric motion, and that allowed to tackle the problem of the filtered equation that will remove some of the difficulty that one had with the equation. So von Neumann, just after the war, had a computer, and he was looking for application. He thought that weather forecasting would be a great useful application, and aviation was developing at the time, so needed for weather forecast, so that provided the push for the development of numerical weather prediction. And Charnley, Fjordhoff, and von Neumann succeeded in integrating the equation, not in real time, but it was a proof of concept that it could be done. And these were filtered equations. Later on, Norman Phillips succeeded in integrating the primitive equation. And there was some other progress later on by Marchuk, who developed something like a split implicit method, and also later variational data simulation. And there was a Canadian contribution. There was André Robert, and for his PhD, he solved the problem with spectral modeling. People could not solve, had problems representing the wind with spectral, with spherical harmonics. And he found a very simple trick that allowed the spectral technique to work. And later on, he developed a very semi-implicit time integration algorithm that was a little bit, he was inspired by Marchuk, but it allowed for a very faster integration of these equations, and the technique was taken on by a few countries, including CMWF. And later on, well, as a minor work from his point of view, he developed a very efficient filter at the time that allowed climate prediction to go beyond 200 and something days, because every model was blowing up by then. So he went to do some administrative duty, and when he came back, well, he came back with the idea of coupling the semi-Lagrangian, the Lagrangian technique with the semi-implicit time scheme, and he produced a very successful semi-implicit semi-Lagrangian scheme, which allowed the use of much longer time steps. And at the end of his career, he developed a fully non-hydrostatic model of the atmosphere that would be able to forecast at any scale, even at the scale of a device that you put on an airplane, for instance, or weather. So, and then the other culprit was Andrew. Andrew came at RPN a little bit before I did, and at the time, well, he was young, and at the time there was the need for high resolution but very quick forecast, like let's say like an outlook that will be on the desk of the operational forecaster very soon. So given the length of the size of Canada, there was a problem of timeliness. And finite elements were new ideas in NWP. I think they had been worked by Mike Cullen and Jürgen. He's not here, sorry. But they were the pioneer of the technique. And nesting already existed for what's called the LFM, but it was shown that there could be problems with the boundary condition with hydrostatic models. So, and the errors would propagate and contaminate the interior very quickly. And also, Canada, for some political reason, was not in the business of doing global forecasts. Therefore, they restricted themselves to using a spectral hemispheric model. Oh, there's Jürgen. A spectral hemispheric model to do the forecast, the global forecast or the hemispheric forecast. So, putting all that together, he came up with the idea of using a variable resolution finite element model of quasi-hemispheric extent with well-posed boundary condition. So that was the origin of variable resolution in Canada. So the initial formulation was by Stanley Fort and Mitchell. Here's the type of grid. The circle, there's the equator. So that was one of the original tests. So the idea is that you would do an accurate forecast for this region. This would be like a buffer region, and you really didn't care if you made any errors outside this area because they would not have had time to propagate inside. So that's the philosophy. So it became operational in '85, and a bit later there was some semi-Lagrangian experiment with the barotropic version of the model again, with Clive Templeton, and eventually a baroclinic model came up, was developed in '89. That was in operation until '97, and that paved the way for the next model. So the next model was what's called the global environmental multiscale model. So there's a multiscale. So the idea here was very bold, was that from global scale, climate, or mesoscale, you could use one global model and just focus the resolution where you needed it. So first so I did this work with Andrew. First we converted, we wrote a very efficient 2-time level global spectral model with semi-implicit semi-Lagrangian. And so we could have built the baroclinic version on that, but we decided that spectral technique had no future. So we converted the spectral to simple finite element. So simple finite element and finite difference are not very different because we are on a Cartesian grid. So linear piecewise finite element and finite difference are not. I mean, you can write everything in finite difference if the mesh is uniform. But with the variable length mesh, it's better to formulate it in terms of the variational principle and everything. Then we built up the baroclinic version on that with a switchable hydrostatic, non-hydrostatic possibility. So it was in pressure coordinate, but we arranged so that just by adding one equation and a few coupling terms, we could enforce or not the hydrostatic balance, hydrostatic condition. initially there was no staggering, and but when we went to the baroclinic version, we found out that we needed some horizontal staggering, so we picked up the C-grid staggering. And also, we found out that there was some noise and instability with the physics, and it was better to control that with an iterative Crank-Nicholson scheme. And fortunately, only one guess and one iteration are enough. Later, we devised, by popular demand, we went back to limited area, but by this time there were enough progress, and it was not pointwise forcing on the boundaries. We could use the semi-Lagrangian approach that we minimize some of the effect of just pointwise forcing at the boundary. And finally, so the last two things, we had no staggering at all, but with this limited area version, working at much higher resolution, it turned out that it would be beneficial to have the Charney-Phillips type of staggering in the vertical as well. So every time we had second thought, that meant going back, and as the model was expanding application, then it meant going back and retrofitting all these changes. And finally, somebody had the idea, well, limited area forecasting, why not just also pilot the nested model with in the vertical? So it's getting close to grid adaptation in 3D. But that's very interesting, because when we use the high resolution nested model, we don't really care about what happens in 2 weeks' time in the stratosphere. So if we do a good job of nesting in the vertical, then we can put higher resolution near the ground. So that was the motivation there. So here are the various configurations that existed until recently. And of course we could rotate the mesh and put the window wherever we thought would be useful. So here's what the scale in time and space that the model could tackle, and the application. So as you see, that was a unified modeling and forecasting system. It did also regional climate. So the current version of the Canadian regional climate is running with GEM. But in gray here, it's we have not touched yet. So there is a project, but climate works on a longer time scale, so it's not completed yet. But eventually, it might be unified. So here's two examples, for instance, that we use the variable resolution for very, very focused resolution over, in that case, over British Columbia, and also with this type of mesh here for continental scale forecasting. And but meteorologists who are interested in these local area forecasts, they say, well, we don't want to care about what's happening in Antarctica, so can you give us a limited area model? So finally did, but okay, I'll come back to that. So the model for formulation I mentioned before. Whoops. And some of the model features, well, because it was semi-implicit, meant there was an analytic problem to solve. As you can see, if you set up a model in that case, a model is made up of these little blocks that can be all put together, and that becomes a baroclinic model. So first you have to worry about solving an implicit problem on the grid that you have. Semi-Lagrangian means that you need interpolation and trajectory computation. And full implicit means that you have to iterate over all of that. So finally build this limited area modeling, and well, we use it in some of the field experiments that were done to validate parameterization or a process, so this would provide guidance to the field. And also, we had quasi-operational forecasts that were done, even though the model was not operational, at least it was distributed and people, if they had time, could look at it. And one of the success was it was used at 1 kilometer resolution over the Vancouver area, BC, for the Olympics in 2010. And later on there was a meeting of G20 in Toronto, so it was relocalized over there just for security reasons to make a forecast of that region. Okay, here's the example. So there are, as you can see, Canada is a large country. So each of these windows you can put UK in it. So we have 4 or 5 windows that we can put. And actually our first test case in the operational meteorologists that were engaged with us, that were very keen, were from this highly mountainous area. And so they provided us with good feedback, and it was a good proving ground for the model. So here's the example of topography, and you probably remember the old Olympics. So eventually, well, you want to cascade to 1 kilometer, so you have to go from the regional forecast that was done with the stretch grid at 15 kilometers, then redo a large limited area forecast that was using the same physics as the 1 kilometer model, and then come down to 1 kilometer, just to minimize shock, because there was no special initialization. And here's the operational scheduling. So you have to worry. This is the constraint that you want the product to be on the table of the forecaster at this hour. So you know that you have to start this one. And in this case, there was some parallel processing going on, because you could send the result of that model to that fine scale model before the forecast was completed. And it was done twice a day. And the conclusion was, well, the conclusion of having this model was that the forecaster liked it a lot, and they would complain if it was pulled away, which was a very nice situation, because when I came into the service 30 years ago, when I was telling people what I was doing, I said, well, I make numerical weather prediction guidance for the forecaster, so the forecaster get it, they take it, put it in the basket, and hopefully, well, there are 2 things. Models have gotten better, and the forecaster don't have enough time to improve on the model. So the combination of the 2 is that they don't throw the models away anymore. So it was a learning ladder for the higher resolution, and eventually the Olympic configuration will be ported to all these operational windows, and it will become fully operational. So So lastly, the model was developed for a composite grid, yin-yang. And this is an idea that came up from PD on the sphere in Yokohama. And I found it interesting because it was addressing one of the problems that we had was it was creating more or less a uniform resolution and avoided accumulation of points near the poles. And it would lead to easier parallel computing. So the only problem is that you would exchange the problem of the pole with the problem of the scene. So these are two rectangular patches glued together and they cover the sphere and they can overlap. So recently we had a paper making a comparison between the lat-long and the yin-yang, and at the same time, since we are developing an icosahedral model, we also compared with it. And for the control, we just reintroduced the spectral operator into the model, at least for the barotropic model, it was easy. So that all the finite difference are replaced by spectral operation. So it's like, so we use that as our control. So it has everything except the horizontal discretization. And I'll show here two of the cases taken from the Williamson suite of test case. So here's the mountain, and here's the spectral reference solution after 15 days. And here I show just the difference between the spectral reference solution and the lat-long grid that run at lower resolution, or at lower resolution even. But it was run with the specification of the Williamson case. And there's the yin-yang. So as you can see, the picture, the difference are very similar. Well, the icosahedral is not doing that well. That's because the test case is set up for in lat-long, and it's very sensitive to the position of the mountain with respect to the position of the grid point in the icosahedral grid. So difference are a little bit larger here. And recently, hot from the press, there was this dynamical core intercomparison project at NCAR, and we had two models to ship them, and this was the work of Abdesamad and Vivian. So Abdesamad actually is the one that was really motivated and picked up this idea and developed it. So he knew enough, actually he's an expert in parallel computing, and he's getting better at meteorology. And he thought that this was a good workhorse, and well, he believed in that situation, in the future of the yin-yang, especially when I told him so. And he did a very good job, and very quickly the model went from research, an idea in Yokohama in 2004, research in collaboration with universities, and implementation probably next year. So here is a random picture taken from a 78-page report, and basically this is just to illustrate how yin-yang and spectral or finite difference give basically the same results. And these results were shown in Potsdam at the last PD in the sphere, and but they are based on real data case, and they show that the models are equivalent, and even for precipitation, which you would think that this is linked to very sensitive physical parameterization, but it doesn't show in that field. So we are pretty confident that it would work. So the conclusion with this intercomparison is that yin-yang is equivalent to lat-long. Yin-yang is more efficient because it takes less points to cover the sphere. There's a more uniform resolution, and it's better to parallelize. So there's a a better outlook for the future. So we expect that we are now running with another 1,000 processor for the operational forecast, but we expect that the lifetime of the model is such that it should work with 100,000 processor. There might be a potential problem, but it was not shown even in the precipitation field. But so maybe this is an anticipated problem that does not occur. Unfortunately, the plans are the variable resolution global will disappear, so it has been replaced already by a large limited area forecasting system going from Japan to somewhere in the Atlantic. But we expect eventually that the global deterministic forecast will be accurate enough that we don't need the continental forecast anymore. And the non-hydrostatic model will become operational, and eventually we should merge all these windows to make a continental forecast at high resolution. So we have developed also global and regional EPS, and the plan is to have, along with the 4D VAR, mix it with ensemble data assimilation, and eventually only ensemble data assimilation. So variable resolution, so rest in peace. So there were two criticisms, because they were already mentioned, is that people working with the physics parameterization, they don't like elongated elements, and when we ran with high resolution, we were producing these elongated elements, and even though there are some answers to that, it's not a problem for forecasting. And if you do a smooth variation of the resolution, it's not that much of a problem near the area of interest. And a filter exists that would remove the anisotropy that would be in the field. So, but operationally, it was decided to remove it. And the other criticism is that physics is not tuned from multiscale, and we have heard the the mention of scale-aware, resolution-aware physics, but physics modelers are reluctant to that. They have a pet resolution, and that's where they feel comfortable. And it was hard to convince them to, let's say, have some dependence of some of the crucial parameter of the parameterization. But in our experience, physics parameterization are much more robust than what the modeler pretend. For instance, initially we were using Manabe convective adjustment, and it took a lot of effort on the part of the physical modeler to beat Manabe, even if we were working at much higher resolution. And finally, another answer to that is that there is also a possibility of blending parameterization, but then of course that increases the cost. So in the future, I think that variable resolution with the hexagonal grid may have a better future. So you will have work there for a few years. Well, at least static variable resolution, and eventually I would suggest to put adaptivity in that local area first, and then global adaptivity later. And for acceptance by meteorologists, it's very simple. you have to show that there is a spectacular improvement, which will not be the case, but you can show that you get the same thing at a much reduced cost and a better outlook for the future. That will be the selling point, I think, of the method. And well, the problem is technology transfer from research to implementation. So I think you have to have well, first of all, you have to have people from the meteorological community that are well connected, that would buy on this idea, and then have collaborators in university that do the development of the idea until they get mature enough, and then bring back these things to fit the format of the Meteorological Institute. And so what's needed is a small but well-motivated team with a correct mix of expertise. And one could still dream of picking a code off the shelf and running atmospheric model, but I think from what I hear today, it's not for tomorrow. So with that, I will finish. Thank you.
Three very quick questions. We're quite a lot over time.
One quick question. How come you went with the yin-yang grid rather than, say, the cube sphere?
I know Mark said one day, I have to remember that. He said the most natural way to discretize on the sphere is with the cube sphere. No. The reason was I didn't like the corner and the kind of coordinate transformation, but maybe in the end it would not have mattered. Also, connected to that, with this two-piece grid, you kept a simple lat-long grid. It's lat-long on each of the faces. One is just rotated. So we already had all the machinery. So it's one of the reasons why it was so fast to develop. And also we could concentrate on the difficulty that was having an intuitive method that worked with this yin-yang grid. And we were fortunate to have an expert on domain decomposition in Montreal at the time, Martin Ganzer. And so we collaborated with him, and we came up with very efficient, you can have practical convergence in very few iterations. So, and we still haven't implemented the most efficient boundary condition there is, because since this system, one grid is embedded in the other, one is providing the boundary condition for the next. So you can generalize the boundary condition to make it thick enough so that it would converge very fast. So that was the reason.
Thank you very much.